Welcome back friends. Today we are going to see steady state analysis of feedback control system. So let us start with an example. Our example is for a unit feedback control system having forward path g of s is equals to 10 in the bracket s plus 1 upon s square in the bracket s plus 2 into s plus 10. So we have to determine first one is type of system, then is error coefficients, and the last one is steady state error for r of t is equals to 1 plus 4t plus t square by 2. So this is the total input. R of t is the total input given. So let us move to the solution. It is given that g of s is equals to this function and h of s is equals to 1. Why? Because it is a unit feedback system. So that's why h of s is equals to 1. So first of all, type of system. Since the s over here carries a power 2, so hence it is a type 2 system. This power decides the type of a system. If s to the power 1, then the type of system will be the type 1 system. Now we have to calculate error coefficients. So first of all, we will calculate the position error coefficient. Position error coefficient is given by limit s tending to 0, g of s into h of s, which is equals to limit s tending to 0, substituting the values for g of s and h of s, and by putting limit s tending to 0, we will get kp is equals to infinity. Then doing the same thing in kv. kv is our velocity error coefficient. It is given by limit s tending to 0, s into g of s into h of s, right? Then substituting the values for g of s and h of s. Now as seen in this equation, this s will cancel with s square, but still one s will remain in the denominator, which will again contribute to the value of infinity. Then moving on forward, Ka. Ka is the parabolic, it is for parabolic input. It is also known as acceleration error coefficient. So acceleration error coefficient is given by limit s tending to 0, s square, g of s into h of s, substituting the values for g of s and h of s. And in this case, we will see that this s square will cancel with this s square. And on substituting for limit s tending to 0, if this in numerator it will become 10 into 1 is 10, in denominator it will be 2 into 10 is 20. So it will be 10 upon 20, so which will be equals to 0.5. Now moving on to steady state error for step input ESS1. It is given by A1 upon 1 plus Kp. So from where did we get this value for A1? A1 is the magnitude of step input part from total input. So as I told earlier that this R of t is equals to 1 plus 4t plus t square by 2 is our total input, right? So consider this equation. Total input is 1 plus 4t plus t square by 2. So A1 is equals to 1, A2 is equals to 4, and A3 is equals to 1 from this equation, as step input magnitude is constant term, right? So in this equation, constant term is 1 for given total input. RAM input magnitude is coefficient of t. Coefficient of t is 4, so it is A2. And parabolic input magnitude is coefficient of t square by 2. So coefficient of t square by 2 is 1. Steady state error for ramp input is given by ESS2 is equals to A2 upon KV, which is equals to 4 upon infinity. It is again 0, and in this case also 1 upon 1 plus infinity is equals to 0. Then steady state error for parabolic input, it is given by ESS3, which is equals to A3 upon KA. Substituting the values for A3 and KA, we will get ESS3 is equals to 2. Now the complete steady state error. So the steady state error for this system is equals to steady state error for ramp input, step input, and parabolic input. It is the addition of these three. So adding them up, we will get our final answer as ESS is equals to 2. So this is our final answer. Friends, keep watching our videos and subscribe to our channel for more videos. Visit our site card2galaxy.com for free notes and PDF. I hope you all have understood this concept.